Hey, and welcome back one more time to AIT 2101, the vibration analysis lecture. And again, vibration analysis is just one tool in our toolbox of predictive maintenance. It couples up very nicely with oil analysis and thermography, and also sometimes ultrasonic detection. But again, it's just one tool in the toolbox, and we're going to continue a little bit more as we talk more about predictive maintenance and how vibration is part of that. Now, we've taken our data. We know how to upload it into our software, and we understand that the frequencies, the amplitudes, the velocities, the accelerations. We understand all these things and how the vibration is occurring, what's causing it to occur, and then of course when it occurs, we read that, and now we've got to discern and kind of decipher, what does this data mean? What is it telling us? Okay, and that's where it's critical that you understand what the data is saying to you, so that you can accurately pinpoint a component that is failing on us. Okay, and then you can trend that data and hopefully be able to predict. Okay, it's going to last about another 3 weeks, another 2 months, or whatever the case may be. And it gives you an opportunity to plan and schedule the maintenance, which is far more economical than reactionary maintenance, where you have to oftentimes have overtime. You're down unexpectedly. You have to explain that to your customers who are waiting on products that are supposed to be coming out of these machines that are now down for the count. Oftentimes you have to fly components in, and freight, your hotshot freight, very expensive. So all these things roll in together. And also, whenever you work overtime, studies show that most industrial accidents happen during overtime hours. So all these things roll in together, and vibration analysis can help eliminate a lot of the excessive costs. So let's try to start making some sense out of this data. All right. So first of all, we know that we got vibrations going on at all kinds of different frequencies. Okay. This is excuse me. This is 1 time, so we got an out of bounce. We got a chunk missing out of our shiv right there. So our machine is vibrating at 1 times the RPM of the motor driving this shiv. Okay, we have bearing frequencies. We talked about inner race frequencies, outer race frequency, ball spin frequency, cage frequencies, and things like that. So we got all these different frequencies that a machine can vibrate at, and that's information. So we got all these different types of information that can be thrown at us. So we got to understand what it is we need to look at and what's most important to us. Okay, so like I said, one machine can vibrate at different frequencies, multiple frequencies. 4 of the most important ones, though, are the synchronous frequency. We're going to break each one of these down. The synchronous frequency, the subsynchronous frequency, the fundamental frequency, and also the predominant frequency. Okay, so let's break each one of these down real quick. Okay, so the synchronous frequency occurs at 1 times the running RPM of the machine. Now we've used the 3-phase electric motor, most of which run at about 1800 RPMs. So if we have a motor, and again this is a motor and shiv combination, by now it can be anything. It can be an industrial blower, it can be conveyors or whatever. But if we have a motor shaft turning at 1800 RPMs, okay, and we have a 1-to-1 shiv ratio, okay, and we have an 1800 RPM frequency coming out of our machine, it's going to occur at 1800 because there's a 1-to-1 ratio between the shivs. The motor's turning at 1800 RPMs. Well, so is the fan shaft. Okay, so we're saying that frequency is synchronous to our driving speed, which is coming from the motor. Okay, so you could have an 1800 cycles per minute frequency coming out of the motor. But if you have a more elevated one coming at the 1800 RPM, you'll know that it is the synchronous frequency of the machine. So, and a lot of times we will pull the data up, and again, this is sort of like what you'll see when you upload the data into the software, and it gives you a spectrum or FFT, a fast Fourier transfer analysis of the data that's been collected. In this particular case, if you had one that's running roughly 1200 cycles per minute, okay, that motor, some motors can run 1200 cycles, okay, but this frequency right here is running 1200 cycles per minute. All right, so we would expect that our synchronous speeds on the other components to run as at 1200 cycles per minute as well. Okay, So, but you can also have a subsynchronous frequency, because those are frequencies that come at lower than the driving RPM of that motor. Okay, for example, using our shiv example again. So we've got a motor shaft turning, let's say 1800 RPMs, and we have a 2-to-1 ratio, whereas the driven shiv is twice the diameter of the driving pulley. Okay, so we're running at 1800 RPMs theoretically with this motor shaft speed 18, and we have a 2-to-1 ratio. That means that our driven pulley, perhaps this is running the fan. Okay, that means that our fan is going to have subsynchronous frequencies coming out of it. If, like for example, if it's one time, so if we have an imbalanced fan, then we can expect to see the imbalance to show up at 900 cycles per minute, okay, on our spectrum. And that's because it is running at half the speed of the motor. So again, our motor is our synchronous speed, and if we have a vibration frequency lower than our synchronous speed, it's known as our subsynchronous. And so that sort of helps us detect if there's a machine, we put our accelerometer on our base, and we see the most vibration coming out of our machine at 900 cycles per minute. Well, chances are we're not going to find that in the motor, because the motor's running at 1800. It's not going to have a frequency lower or vibration at a lower frequency than 1800. Okay, if we got our accelerometer just like on the base of that machine, and we see it vibrating at 900 cycles per minute, we kind of eliminate the motor, and we know that the fan's running at that speed. Okay, then the fan's our problem somewhere in our fan, and because of the fact that it's running at 900 cycles per minute, that's half the speed, but it's also 1 times the speed of this fan, half the speed of the motor, but 1 times the speed of this fan. We know we probably have an imbalance of 1 times the RPM shows up as an imbalance. So we got probably an imbalanced fan. Okay. So anyway, that's the sort of the definition and explanation about subsynchronous speeds. Okay. And in our spectrum, again, once we download it, for example, here is our 1 times, which is our this is our 1 times our motor RPM right here, 1800, and here is our half speed of our motor, which is 900 cycles per minute. And you'll notice that this peak right here is much higher than this one. And so it gives us an idea that we got a bigger problem right here at 900 cycles per minute. And going to our previous example, we go ahead and dial in on the fan. We can eliminate the motor, okay? And the fact that we're running at the frequency is heaviest at 900 RPM, we can eliminate bearings too, because they're going to have a higher frequency because they've got multiple balls spinning in there. We'll get into that just a little bit too. But this spectrum gives us we look and say, okay, what runs at 900 RPM on this blower unit right here? Well, the fan does, so we just dial in on that and we eliminate all the other stuff. Like I said in one of the previous lectures, it's kind of a process of elimination, and this is where we start eliminating everything. This is where we're starting to dial in, and this is where we start to identify the component and know exactly which one or what the problem really is. Okay. Then we have our fundamental frequency. Okay. That is the lowest or the first ordinance or order of frequencies in a particular component. Okay, you use these a lot in bearings and gears. Okay, again, the definition is the lowest or first frequency is associated with a particular component, problem component. Okay, let's use the graphics here for just a minute. Here we have our industrial crane, our overhead crane gearbox. Okay, and this is sort of like, this is not exactly like a gearbox, but it's the closest one I could find. What we've got here is we have our input shaft. Our motor would be coupled to this input shaft, okay? And these gears, this gear is driving this gear, and this gear is driving these, and so on and so forth. So you can look, you've got multiple gears and multiple gear ratios going on, and that's all in that one box. Well, how that's important is if you have a damaged gear right here, that gear may be different from this one and this one and this one and this one. So it gives you an idea of which gear do I need to replace, or which one do I need to order. Again, we're all about planning, and we don't want to take us down any sooner than we have to. So we want to know which gear do I need to order. Well, we can identify based on the gear mesh frequency of which, like it's got an defective or chip tooth there on the gear. We can identify which gear based on the speed at which that vibration is ringing out. That's all derived That's all derived from our input shaft gear, that very first gear, and that gives us our predominant frequency. Now, go a little bit further with this too. Our predominant frequency is derived by a simple formula. We take the motor shaft, the motor RPM, or that driven shaft RPM. You typically don't couple a gear and a motor together through a belt or anything like that. It's a direct couple. So if we're running our motor at 1800 RPMs on our input shaft on the gearbox, then we can take that and multiply that first gear by the number of teeth on that first gear by the speed of the RPM, or the RPM of the input shaft, okay? And that gives us our fundamental gear mesh frequency. And in this particular case, we've got 1800 RPMs, we've got a 20-tooth gear, I'm just using a number out of the air. So say this gear's got 20 teeth on it, then our fundamental frequency, or our fundamental gear mesh frequency for the gearbox is going to be 36,000 RPM. Now, all the other frequencies, and I'm not going to go diving deep into these with a lot of calculations, because I'm not trying to make you level 1 certified or anything for this, and you really would get into these calculations going for level 1 certification. But this is an introductory part, but I'm trying to show you that all other frequencies of vibration, if this tooth is chipped, or this one, they're all derived from that fundamental frequency that we calculated on that first gear. Remember, we said that in the definition, we said it was the lowest for the first frequency associated with a particular problem, okay? Well, it's going to be based on that first gear right there. So our fundamental gear mesh frequency is going to be based off of that right there, and multiply it by the speed of the input shaft, and then you can start to figure out all of the other frequencies. And they would normally show up like this on your spectrum, and I know you can't see this on the screen, but here, if you remember, on our first slide, we had a predominant frequency way down low. That was 1 times the RPM. Then we had a heavy spot in that fan at 900 RPMs, okay? So that 900 RPMs is way down here on the spectrum. However, when you're looking at, say, 36,000 at our gear mesh frequency, okay, and of course these are cycles. This is the frequency line down here. This is the frequency axis, and around the 36,000 right there is our predominant frequency. Our gear mesh frequency. So we wind up with our spectrum showing a much higher frequency than we did back here at 900 when we just had a fan out of balance. Okay, here we're looking at gear meshing because there's a lot more teeth involved. You know, the meshing, each time a gear meshes with another one, you've got multiple teeth on those gears, so your frequency is going to be greater. And so this starts to show up about right here in the 30 to 50,000 cycles per minute as far as gear meshing. And it's going to vary depending on how many gears you've got in there, how many teeth does each gear have on it. But this gives you an idea that you're not going to find your gear mesh frequencies down here around the 900, 1800 cycles per minute. You're going to find them much higher, okay? And then finally, the predominant frequency, okay? The predominant frequency is the frequency we need to worry about the most, okay? Which one is the highest, okay? It will not always be the one on the far left, like I showed you right there. This, you know, most vibration does come from imbalance. You know, so this is your lower cycles per minute, so it's going to be on your left-hand side. And most of the vibration that we run across is a result of imbalance. However, you see these peaks right here that are much higher, you know, further down in the spectrum. This could possibly be a gear mesh frequency or something too. But my point is that the predominant frequency, this could very well be higher in amplitude than this one. And it's the one that we're looking for that's got greater amplitude, that's our predominant frequency. That's the one that's given us the most amplitude of our vibration, and that's the one we want to be concerned with. Okay, so that's what we call our predominant frequency. And again, those are the ones that gives us an idea of when the damage is the most severe, and it needs our attention first. Now I want to go back earlier, just touch base on this one right here. We got our ball spin frequency, and we talked about the gear mesh frequency being in the 30 to 40, 50,000 cycles per minute, possibly. And again, it's all dependent upon the number of intermediate gears that are in there, the number of teeth each gear has, the RPMs at which the input shaft speed. All of these vary greatly. But even a higher frequency would be a bearing frequency, and that's dependent on the number of balls. It depends on how many balls the bearing has, the diameter of the ball, the radius of the ball. All of these things come into play. How fast do we spin that shaft, and how often are the balls passing over a defect in the inner race or the outer race. A lot of science goes behind it that you really don't have to be able to collect the data, but enable to interpret the data. It really helps to know and understand, okay, I've got this frequency out here at 70,000 cycles per minute. What is that? Well, it gives you an idea, hey, that's the bearing frequency. We need to start looking at that bearing. And we're not going to mess with opening up a gearbox, because the gearbox is not the problem. The bearing or something else is the problem. So again, it opens up a lot of information for you when you know where on the spectrum or how many cycles per minute that vibration is occurring. So wrapping up real quick, recapping, okay? We know everything vibrates. Whether you realize it or not, I'm just standing right here, this building is vibrating. It's just part of the Earth's movement. Transit vibration from trucks going down the highway back here, a quarter of a mile away. That vibration just doesn't go away, or just not. It transmits through the Earth. Okay, so everything vibrates. Okay, as a matter of fact, we talked about electrical signals. How many of you have ever had a light bulb get loose in your socket of your lamp? Okay, go in there and tighten it back up. Light comes back on. How did it get loose? Well, remember we said that our electrical cycles are going 60 cycles or 60 hertz, which is 60 cycles per second. Okay, that is literally a vibration. You're peaking, and it is a vibration going on there. A lot of times you can hear a hum from a transformer. Those are the cycles going through that transformer. But going back to our light bulb example, that is a vibration, and as a result, it's vibrating that light in that socket. Well, as that socket, as it vibrates, it's following those threads on the base of that light bulb, and it's not going to tighten itself up. It's going to go past the least resistance, so it's going to loosen itself. So when you run across the light bulb, it's a result of that electrical vibration, the harmonics in the electricity in the AC cycle. That has an impact. That's a physical vibration that literally will loosen the bulb in that socket. So just a little tidbit of information to let you know that everything does vibrate. Okay, machines have multiple frequencies in which they vibrate, or which they transmit or emit, I should say. So a machine can have multiple vibration signals. Okay, one time's typically in balance. You can have misaligned couplings that are 2 times, and we'll talk some more about these in the lab. You can have as we showed, the gear frequencies, the gear mesh frequencies in a gearbox. You can have ball spin frequencies, inner and outer race frequencies that are within a bearing range. So they all have everything has multiple frequencies as far as the machines are concerned. Okay, frequencies can help pinpoint the problems, and believe me, that can make you look great or really bad at what you're doing. Okay, understanding the frequencies and what they are trying to tell you, that's the information they're trying to tell you. You can identify a bad component, and it actually be good if you don't know and understand what frequencies are coming out of there. Okay, the amplitude tells us about the severity of the problem as well. How much is it vibrating? Okay, so it's vibrating. Great. Okay, it's fine that a fan vibrates at a certain cycle per minute, or excuse me, at a certain amplitude. But it's not so good if like I said earlier, a lathe or a mill is vibrating at that same amplitude. Unacceptable, because we're trying to make very tight tolerance parts with that mill or that lathe. All right. Also, trending. This is really important. Trending this vibration data. Okay, you get your baseline data. You remember me talking to you about that one fan bearing that I had go bad over the weekend when it wasn't even running. Well, I was getting my baseline data. And from that point, I'm going to watch that bearing over a period of maybe even a couple of years. We saw the life expectancy of bearings and things. So I'm going to trend that, and I can watch it. Now, it will trend, and also it'll go exponentially worse. But I'll watch that, And as that starts to increase in vibration levels, I can say, okay, based on what I'm seeing over time, we probably need to get that bearing flown in here, or not flown in, but shipped in here. And we need to plan our maintenance because it's a lot cheaper than if it were to fall apart on the job. And remember, we talked about collateral damage, and there's safety involved and possibility of loss of life. Okay, so all of this can be avoided by trending the vibration data. Okay, and that really makes you look good too to your immediate report. So anyway, it gets you out of a bind too with some of the mechanics too. But and planning the corrective action is much more economical. We've talked about this too. You got your overtime, you got your safety, and when you're working overtime, that kind of the safety part starts to go down from there, and more accidents occur during overtime. You've got to fly components in often, or hot shot them on the ground, scrambling. You've got a lot of resources looking to try to find those components, okay, that you're expending. Then you've lost the production out of that machine. Not only do you lose the money that creates, the revenue that creates, but also you've got some credibility issues with your customers as well. So all of these things roll together globally and give us, the costs are just more exponential as opposed to us being able to plan our maintenance based on the data that we've been collecting through vibration, oil, and thermography. Like I said, vibration is just one component, one tool in our toolbox. So anyway, that's our recap. I hope that you have learned a little bit out of this vibration series. Again, if you have problems or you have questions or concerns, or if you want to share a vibration story with me, by all means, let me know, okay? But anyway, that's our vibration analysis. Hope you've enjoyed it. Hope you've learned it. Thanks again for watching, and we will see you in the lab.